in Lagrange mechanics. You write the Lagrangian and you find Euler-Lagrange equations, yes? By variation. It seems like that. It seems that this logarithm works like Lagrangian for you. And these variables are like coordinates, like Q1, Q2, Q2. And then the equation which you will find is like Euler-Lagrange equations. So this is a principle of action actually here. Okay, I need to complete this calculation, so that's it easy just for you step for us. So that should be 0, huh? That should be 0. So if you want to be 0 for each parameter should be 0. We have a partial derivative here, huh? With respect to n1, with respect to n2. So this is will be 0. So logarithm nr minus beta here r minus alpha. Easily from here you can just make the exponential. Can I write this, because I don't know what is the alpha, but can I write that just C0 is a constant? This is the answer. How I can find the C0? Still we have a two constraint, look. That should be sigma n. This chapter is the core of the statistical physics. Is the core. All the chapter after that use this. Even all the result of previous chapter you can find with it. The only way to learn that is one time to do all the calculation yourself. Maybe more than one time. Just ask the same question I asked you and answer them yourself, by yourself. Don't look at the notes or something. Try to solve that from the beginning. Anyway, I find the C0. So we are in very good condition because we already have this. This is very beautiful actually. Look, this is the NR. That gives you exactly the number of the particle which needed to sit in each energy state. Just give me the energy state, I will tell you, and total number I will give you how many particles you need to sit. It doesn't look like the 1/5 or 1/3 or 5 or 3 or 4, because the energy state continues now. Energy start from 0 to infinity. It's not 1, 2, 3 like this example. Isn't it? And what is the probability? I told you probability is the number of the state, number of possibility over the energy here over the total. So I don't make block now, so box. I want to continue one more. This is the Boltzmann equation. So it was the discovery of the Boltzmann, the unlucky person in physics. So he has himself, because he worked on the ergodic theory for a long time, so he didn't get any results of his society, unfortunately. He was very poor. This is the PR. So just remember this, this sigma is, it looks like not very comfortable us. Still I didn't explain you what is the beta. You don't know what is the beta. I will tell you what is the beta. For alpha you understand what is the alpha. E minus alpha is this one. But you never will see the alpha since next chapters. This is called a partition function, this. There are different notation for that. Sometimes they write Z vector, sometimes they write Q vector. Anyway. How I find the, so PR is E minus beta ER over Z vector or Q vector, because I write two notations for Q vector. What is the beta? So for the beta, you needed to remember this equation that sigma ER and R should be E. So let me just write it that here. What is the NR? N over Q beta Can I make it this equation simpler as much as I write here? Yes, because you know the Q beta is sigma E minus beta ER. So just make a derivative of this with respect to the beta by no any reason. So you get ER E minus beta ER. Yes? So the denominator of this one can be minus round beta partial Q beta. Can I write that? One thinks that the Q is function also of n. So we needed to write n here also. Qn. Okay? The number of particles will appear here first. Okay. So this equation gives you the definition for the beta. So beta is related to the energy per number of the particle.
Why we write differential of logarithm Q and P? It's already the same.
Already is logarithm, yes. Okay. So alpha is related to the number of particles and beta is related to the average of the energy. Energy per particle. Energy per particle is given some function of beta, I know. You cannot find the beta explicitly from this equation, but just give you beta in terms of the even there. So just let me to summarize what I find it here. So, and using this PR you can find everything. Everything you can find it from here. So the canonical partition function is sigma E minus beta ER. Next chapters you will learn that this is actually the trace of the some type of the operators actually. If this is Hamiltonian actually, and this is called trace. But I don't repeat this here. So this is just the partition functions. And with this partition functions you can almost find whatever you like. For example, the the energy per. Okay. Because this logarithm appears many times, this logarithm.